So before we even define what continuity is, well, maybe I should define it. So continuity of function is continuous if I graph the entire function without lifting my marker off the paper. This is a continuous function on all real numbers. So when a function is not continuous, when? So here's one situation. So here's a graph of a function. Obviously, I had to graph this piece and jump up here and continue. So of course, this is called a jump. So a function is not continuous if it has a jump. Good. A second possibility, which is a very important type, is this. With or without a point, a full point there. With or without. It doesn't matter. This is called removable. So with a point or without. This graph or with it. It's a removable discontinuity. This is a jump discontinuity, removable discontinuity. Okay, here's the next one. So here's the graph. This one is called infinite discontinuity. So jump, removable, infinite. So now let's take a look at this function and this point P. Will you say that this function, f of x, is continuous at point P? Would you say yes, or would you say no? The function is not continuous, or the function is continuous at P?
It is continuous.
Continuous at P. Why? Since the limit as x approaches a, of course, this is my a and this is my f of x. As x approaches a from the left of the function equals the limit as x approaches a from the right of the function, and also equals f of a. I'm going to write it again. I know it's squeezed in that 1 squared inch. So I'm going to write it again, and this is the title of this. Continuity at a point. A function is continuous at x equals a if the limit of the function from the left of a exists, of course, and it equals the limit of f of x as x approaches a from the right, and it equals the function value at that point. Which makes sense. The limit from the left, the limit from the right are equal. They exist and they're equal. Furthermore, equal to the function value at that point. Okay, we're going to look at a few graphs in a moment. However, I just want to identify one more thing. a function is continuous from the left if the limit as x approaches a from the left of f of x equals f of a. Well, what does that mean? Here's the example. Continuous from the left. Continuous from the left because the tendency to approach this value and the function value at that point both exist and are the same. Is this function continuous from the right?
No.
No.
Of course not. Thank you. It's continuous from the left because the limit from the left and the function value are the same. So it could also be continuous from the right. So here's an example of continuity from the right. This situation, limit Sx, of course, this is a right here, of course. Limit from the right of a of f of x equals f of a. But it's not continuous from the left. It has a limit from the left, but it's not continuous from the left because the function value is not here. And one more thing before we look at examples. Continuity on an interval. So what do you think about this function? Can I say that it is continuous between a and b?
Yeah.
Yes. So continuity on an interval means the function is continuous at each and every point on that interval. Continuous at each and every point. I'll take care of that in a moment. At each and every point on that interval. Good, so my props are handy here. I call them my props because sometimes I cover examples or portions with them. Good, so I would like now to also identify which functions are continuous and when. Polynomial functions are always continuous. Exponential functions are always continuous. Rational, trig, other than sine and cosine, I should write here sine plus cosine, are always continuous because they are defined on all real numbers. Rational functions, trig functions, radical, although the cube root can be added here because it's continuous everywhere, because it exists everywhere. Rational, trig, radical are continuous on their domains. So for example, f of x equals 1 over x. What is the problem with this function?
X can't equal 0.
Perfect. So then we know that the domain of this function in interval notation is this. And it's guaranteed that on this interval, 1 over x is continuous. Guaranteed. Of course, it's not continuous at 0, but it's continuous everywhere on its domain, guaranteed. Okay, that's pretty much all I wanted to say. And so far, and we have to look at the intermediate value theorem in a minute. But I want to open the book right now. I'm opening the book. I have it here. The ebook. And I'm also getting ready my calculator. I'm just clicking on it. Okay. So it's ready to. So almost there, almost there, almost there. Okay, ebook. So I would like us to look at 2.5. I'm sharing my screen. Okay. Two 2.5. Where is it? Why is my computer thinking so hard? Okay, well, I did click. Okay, good. So let's take a look at a few examples. Let's look at a few graphs. You choose, or I will. Any graphs to identify continuities. Okay, let's take a look at this graph. Is this function continuous at -4?
No.
No.
Perfect. What type of discontinuity is that?
Removable.
Excellent. What about a -2?
From the left, yeah.
From the left is continuous. Excellent. Is the function continuous in general at this point?
No.
No.
What type of discontinuity?
Jump.
Very good. The same thing here you're going to say, and it's continuous from the right. And here the same, it's continuous from the right. But now let's take a look. It appears that there is a what at 4?
Infinite.
Correct. It appears that at 4, the function has a vertical asymptote. So this is from the right, from the left, if you want, it's an infinite discontinuity. Okay? Okay. They're all the same. Do you feel like we should look at anything else? So again, the same thing here. Although there is a point, this is an infinite discontinuity. Okay. Next step, I would like us to choose a piecewise defined function to graph. As you see, we can't get away from this. It says sketch the function and then explain why the function is discontinuous at a given number a that is listed here. So let's choose a function, refresh our memory on how to graph a piecewise defined function.
21.
Good. So let me copy 21. Very good. So 21 has f of x equals 1 over x plus 2 for, of course, x not equal -2. And it's 1 for x equals -2. Perfect.
That's 20.
Oops. I do that a lot. Who would like to be in charge? Who would like to be in charge with me copying the correct? I always delegate someone. Okay, so you said 21 and I copied 20. Sorry about that. So f of x x plus 3 for x less than or equal to -1, 2 to the x for x greater than -1, and a equals -1. Perfect. Thank you. So now we are going to start by graphing this function first. And as you know, we will always change this in an interval notation. Can anyone